Approximate Reasoning with ASPIC Plus by Argument Sampling, written together with Tjitze Rienstra.
Okay, thank you, Mauro. Thank you for the introduction, and hello, everybody. So, yes, Mauro already mentioned the title, and I'm also glad that Guillermo, in his previous talk, I hope you all watched that, at the end briefly hinted at ASPIC and how it's going on there. So I may be a little bit briefer on the background information here. So, what's this about? In a nutshell, and this is basically the main approach how you do reasoning and structured argumentation approaches. We are looking at this argumentation pipeline of how you do reasoning and structured argumentation. So we look at settings where we start from a classical logic knowledge base or a knowledge base consisting of rules. And in the first step, what we do there in order to do some reasoning there is we construct arguments. And arguments are basically minimal proofs of some certain conclusions. Now, so we do some rule changing, and then we can get a couple of rules which together imply some given conclusion. Now, like for example, in this knowledge base A together with A implies B. So this arrow can be seen as a strict rule, as a defeasible rule, whatever. These together imply B. Now, so and then we get an argument for B. And this is done in ASPIC Plus, for example, where you also can differentiate between strict rules, defeasible rules, and other nuances. And once we construct the arguments, we can build abstract argumentation framework out of them by identifying nodes with these arguments and adding a text between these different arguments using some form of conflict relation. So for example, if you have an argument which attacks some intermediate rule of another argument, we add an attack between these two arguments. And then we have this graph. We do our stuff we do in these graphs. So we determine extensions, determine what arguments are, for example, credulously or skeptically accepted. We take these arguments, extract all the conclusions out of these arguments, and these conclusions are then the inferences with respect to our original knowledge base. So this is done in ASPIC Plus, for example. It's also done in a similar way in ABBA, and also in a similar way in the newer version of deductive argumentation. Defeasible logic programming is a little bit different, but this is essentially the main pipeline for structured argumentation approaches. So when you come to addressing these inference problems computationally or algorithmically, there are a couple of challenges in here. And the main challenge here is when it comes to structured argumentation approaches, maybe a lot of arguments in the knowledge base. So when you have hundreds of rules, you can combine these rules in many different ways, giving rise to, in the most extreme case, to an exponential number of arguments you can construct from a knowledge base. And then you have a very big abstract argumentation framework, and then you also know we have a lot of problems, a lot of challenges there as well, because many of the most interesting semantics in abstract argumentation frameworks, they are intractable. So then you have two really big problems. So you have to generate an exponential number of arguments, and on this exponentially big argumentation framework, you have to do some intractable reasoning, which is also in the worst case exponential in the size of the framework. So we have double exponential. That takes a lot of time to do reasoning in complete structured argumentation when you follow the complete pipeline here. So in this work, what we are trying to look at, investigate approximation algorithms for this problem, and in particular, address this first step. So we'll not talk so much about how we can do effective reasoning and abstract argumentation approach. We take this for granted. We have some solver who does abstract argumentation reasoning, taking it for granted. But to look at the first step, so when we construct the arguments, is it really necessary to construct all the arguments, or can we just focus a little bit on a smaller subset of that? So this is the outline. I will give you a very brief background section on ASPIC Plus, but it's only very, very brief to get to the main idea. So what we are doing here actually in this work, it's more or less independent of the concrete structured argumentation approach. So it could be done in the same way with ABBA and other flavors of ASPIC Plus, but some basics are in order. And then I will talk about our contribution here. So basically two different approximation algorithms for addressing this problem of this exponential blow up of the number of arguments. And we evaluated these algorithms on some data sets, and I show you some results of our experiments. Okay, so first of all, we will talk about ASPIC plus here. So it's a very general approach to do structured argumentation. And I mentioned that, so I will only give you some very, very simple basics. There's much more to ASPIC plus than I will present here, but it will suffice to getting the idea how in general you do reasoning with structured argumentation. So we here see ASPIC and ASPIC plus knowledge base as a pair of two sets, one set of strict rules and one set of defeasible rules. So and here we assume that all these symbols, so phi, all these phi's and all these psi's, they are basically just propositional letters or negations of propositional letters. So we take a very simple language here. So in general ASPIC, this can be anything. This can be complex formulas. These can be some other logic, first order logic, or some other things. So here it's just basically a very simple formalism. So we have a set of strict rules. Basically the intuition here is if you believe phi 1 and phi n are true, then you have to believe that psi is true as well. On the other hand, we have these defeasible rules. So the difference here is now, so this double arrow, and here's a simple arrow for strict rules. Now for the defeasible rules, the intuition is that if you believe phi 1 to phi n, then you usually also believe in psi. Now, but this could be attacked by some argumentative analysis, and it may not necessarily be the case. So then basically, this is a knowledge base we start from. So we have a set of strict rules, we have a set of defeasible rules, and some of these rules may have an empty premise. So these phi 1 to phi n, this may be actually empty, so n may be 0. And these are basically the facts we can start our reasoning from, or the axioms we call them, if it's a strict rule, or assumptions if we start from defeasible rules. And putting them together, we can form chains of rules. And basically, we say an argument is a minimal kind of set of rules which entails the conclusion. Oh, sorry, this should be a psi. Yesterday I had the same typo, I didn't fix it, sorry. So an argument is a tuple, so with a set of strict and defeasible rules, and this is a premise or the support, and some conclusion or claim psi. And this is an argument if this set A is a set of strict and defeasible rules, and these strict and defeasible rules somehow entail this conclusion psi. Now, so somehow is a little bit hand waving here, but this basically just chaining of rules, and each rule must have a support where the formula appears somewhere previously in the chain. You get the idea how you usually chain rules in these kind of frameworks. It's also not really important. So in other formalisms, this is defined a little bit different. But for us, just a set of rules that somehow entail some conclusion. So this gives you a definition of what's an argument in ASPIC plus or in structured argumentation frameworks in general. Now then it's left, how do we define a conflict, the conflict relation between arguments? There are also different versions how we can do that. So for me here, just take very simple definition. So we say an argument A, so with a support uppercase A and a conclusion psi, attacks another argument B psi prime if the negation of psi, so the negation of the conclusion of the first argument somewhere appears in this uppercase B. Now, so is maybe an intermediate conclusion of some rule in there, or is actually psi prime itself. So there's some point in the uppercase B where we have a conflict. As I said, ASPIC plus can accommodate much more than just that. So we could also, for example, attack rules themselves. So we could invent names for rules and attack these rules itself. But everything works the same if we extend this. This is just for conveying a little bit the intuition. So let's look at an example. So here's a very small ASPIC knowledge base. We have 3 assumptions here. So defeasible rules without support. Now, so A can presume be true, B and D. We have some more complex rules. So from A, we usually derive C, from B not C, from CD, we derive E. And then we can already see, okay, we can construct some arguments here. So for example, if we take A and if we take D, then A gives us C, and together with D we can entail E. Now, so this is an argument for the conclusion E. Now, so from A, from D, A and C, A implies C, CD gets us E. This is the argument for E. And another argument, if we just assume B from B, not C, gives us the conclusion not C. And we can see the latter argument attacks the previous one, because here the conclusion of this argument appears in this previous argument here at this point. Now, so in order for the argument A, sorry for the confusion. So for this first argument to work, we need this intermediate conclusion C, and we attack this with this other argument. So, and this defines us now an attack relation between these arguments, and then this basically gives us how reasoning is defined in ASPIC+. So formally, how's the inference procedure defined in ASPIC+? So we first determine all possible arguments in our knowledge base. So we look at all rules, how can we combine them, what kind of conclusions can we infer, and each argument we identify, we put in a graph as a node. And then for each pair of arguments, we check whether the first argument attacks a second, and if it does, then we add a directed edge. And then we have an abstract argumentation framework. I mean, it's not abstract anymore because we now have some structure in each argument, but we have a graph. We can now use our classical semantics on that. So for example, we can use preferred semantics. So look at all maximally admissible sets so maximum with respect to set inclusion of this graph. Then we have a couple of these preferred extensions. And then we can say, okay, we do either credulous reasoning or skeptical reasoning. So if we took credulous reasoning, we take the union of all these arguments, and they are all our accepted arguments. If we take skeptical reasoning, we take the intersection. Or we just do a grounded semantics reasoning. So there's just one extension, so both of these things coincide. And in the end, it's also important how we do that. In the end, from this graph, we get a set of arguments we accept. But if we have structured arguments, we're not interested in the arguments themselves. We are interested in the conclusions of these arguments. So what we do is we look at all the conclusions of all these accepted arguments, and those are then also the conclusions of our initial ASPIC knowledge base. So we now defined an inference relation from this knowledge base to a set of propositional letters or propositional literals, basically. And this defines the inference relation ASPIC+. Okay, so this is how you do it formally. Very brief overview how you do it. As I said, there's much more into, can be much more into ASPIC+ than I showed you, but this is the essence. So let's go now into the problem of doing reasoning there. So basically what I showed you in the previous slide, so I'll go back, this is an algorithm. So this is an algorithm that works for doing reasoning in ASPIC+. But of course you can see that it's not very intelligent algorithm. I mean, this is a semantical definition. It's not suitable for actually using this in working systems. Because what is the reason? Now, the main problem I already identified, the number of arguments you can have may be exponential in the number of rules you have. Because they are maybe quite complex rules, you can combine them in many different ways, and this may give rise to an exponential number of arguments. And actually, we get a lot of arguments which are not really necessary in order to, for example, answer a certain query. Now, so for example, if you ask for some certain literal like the literal A, is it accepted or not? So you don't really have to look at all possible arguments. You don't have to construct all arguments. And even if you want to determine all accepted literals, there may be many arguments which are more or less equivalent to each other or do not really play a role in determining the answers you may seek. Now, so what we want to look at here is a very simple, so actually two very simple ways to address this problem of this blow-up. And we ask the question, very simple question, a very simple approach I will present here. Does it suffice to not consider all of these arguments, but only sample a sufficient number? And sampling means really doing some random sampling. Now, so instead of constructing systematically all arguments, let's just sample some. So try to construct an argument. Okay, take this one, sample another one, just randomly look through your rules, somehow combine these things in order to construct an argument, and then collect some, do the reasoning afterwards. Now, so just say, okay, my argumentation graph just comprises these very few arguments I sampled, and hopefully the answer will be the same as if we do it in a complete fashion. And so this is basically also already the idea of this first algorithm. So I'll just give you the sketch. The details are in the paper, of course. Now, but very simple idea here. What you can do in order to sample arguments, you just pick a random rule from a knowledge base. You look at the elements in the body. Look in your knowledge base, is there some rule which has one of these elements as the conclusion? Then you pick some of these random rules and repeat this recursively until your argument is complete. Now, so basically, this is a backward chaining procedure, but not a complete one. Now, so you do some random selections in each step. You don't look exhaustively for all possibilities how you can derive a certain element. You just pick one, see if it works out. If it works out, you have an argument. If not, you just start again. And basically what you do, and you do this a couple of times, hopefully at some point you have sampled enough arguments, and then you do the actual reasoning on the resulting sub-framework of the whole framework. Okay, sounds quite simple, but it's actually quite good in our experiment. So for that, we come in a second. So the second approach I want to show you, it's a little bit more query driven. So I already mentioned that if you have already a query, a lot of arguments may not really be necessary for answering a question. So we looked at some more elaborate way, let's say, to sample arguments, which also take into account what do I want to answer in the end. So the previous approach, we just sampled some arguments, some maybe still irrelevant, but we still do it, and it still works quite good in the end. So, but another approach is to make this a little bit more intelligent. So here idea is, if we have a certain query, if we want to ask, okay, here's the literal A, is it accepted or not? So what we basically do is we look first at all the arguments which have exactly this literal in the head and construct them. And then we look at possible counter arguments for these arguments. But we don't add all counter arguments, we just add some of these arguments with a certain probability, also everything independent samples. So this means we get also a couple of arguments, randomly sampled, but we take a little bit into account the dialectical procedure in order to answer the query. Okay. Very sketchy, I think, but hopefully you get the idea. So basically we try to avoid this blow up and just sample some arguments instead of looking at all arguments. And then we ask, okay, very simple ideas, does it work? So does it work in practice? If we look at actual knowledge bases, do we get, what kind of accuracy do we get? So are we good in terms of accuracy? Do we often get the same answer as a complete reasoner or not? So in order to do that, the first thing we had to do, because there was quite a lack on that in the literature, we had to do some nice some good compiling of suitable data sets. Now, because there are no real world ASPIC knowledge bases out there, so we had to compile some ourselves. So what we did is, first of all, did some easy random sampling. So we created a generator which generates random ASPIC theories. So we generated some of those. I can give you details on how it is actually done. It's in Tjitze project if you are interested in that. It's a very simple way to just randomly generate rules. Then as a second thing, motivated from another use case we do where we try to combine machine learning with argumentation. We looked at a specific, quite popular data set for machine learning classification tasks, for association rule learning tasks. This is a very simple data set consisting of a lot of animals with attributes. So are they white? Do they live under the sea? And so on and so on. And we try to learn rules out of that. And we use these rules then actually as ASPIC knowledge bases. Third, we also looked at max set competitions because they also have a lot of instances which are inconsistent, and we try to compile from these instances. So we try to compile from clauses rules in some way and use these knowledge bases as ASPIC knowledge bases. So if you like, I can give you more details on how we compiled that. So, and on these three benchmark sets, we tested our solvers. So our solvers are the two below. So ISAM is the independent sampler, the first one I showed you. Directional sampler is the second algorithm I showed you, and with some baseline approaches. So naive is basically the semantical definition. We construct all arguments, and we also looked at two more realistic baseline methods. So the MB stands for module-based, where we only looked at the syntactic module of our knowledge base, which is important for the query. And directional, which basically is the same as our second approach, but we construct all necessary arguments. So, okay, enough for that. So let's look at briefly at the results for the remaining 1.5 minutes. What I want to highlight here, so you see here for the 3 different data sets, random, animals, and max set. The first 3 lines are the complete baseline methods, and below are our 2 approaches. You see here the percentage of solved instances, the runtime in milliseconds, and the accuracy. Of course, the complete solvers all have an accuracy of 100%. Accuracy meaning how many of the answers are correct, because they are complete, they are always correct. And the first thing you can notice that even if you look at approximation algorithms, the accuracy is quite high. So we are always at 99% and close to that. But in contrast to that, we are quite fast. So it's not really a order of magnitude faster. At some point, it is a little bit, but we are always very fast in compared to the complete algorithms, but we only lose a little bit on accuracy. Okay, so time's up, unfortunately, so I come to the conclusion. So I gave you very simple ideas on how we can do approximation algorithms for ASPIC plus or structured argumentation in general, and the takeaway message is that we gain some improvement on performance without losing significant accuracy. Okay, of course, what we can do apply these things to other structured argumentation approaches in a very similar way. That concludes my talk. Thank you for your attention.